Welcome everybody to Lecture 9, Information Retrieval in the Winter Semester, now 2023. There I said it. Happy New Year. May it be a normal year. A very daring wish after the last 3 years. Let's see. So what are we going to do today? I will say something very briefly about your experiences with the last exercise sheet, which was about the vector space model. About the exam, you should absolutely register because you only have less than a week left. And today we talk about some truly beautiful and amazing linear algebra. You will see what all this means. And the exercise sheet is another pencil and paper sheet. Whether you really do it with pencil and paper is up to you, but it's mathematics, and it's even a special kind of mathematics. It's the computing, calculating part of mathematics. So like 6 times 7 is 42, but with matrices. In the past years, we did a coding exercise here, but that had problems. I will maybe talk about this later, but it's really a beautiful topic. Vector space model. So the last lecture before the Christmas break was pretty lightweight. We did some UTF-8, which was left over from the previous lecture, and then it was a very gentle introduction into linear algebra. Most of you, not all of you, found it relatively easy. The normalization was a bit tricky. Let me remind you, it was just take the second exercise sheet and now don't do it with just do it with linear algebra, with matrix computations, where you can do everything very elegantly. I enjoyed this sheet a lot. It was a very good way of getting back into linear algebra. That was exactly the goal of the lecture. A little bit rusty, this is what I expected, but I hope I can brush it up in the upcoming lectures. I hope that too, and that will also be one purpose, because we will have linear algebra in a number of lectures now. Most of the time spent debugging sparse matrix stuff. Several people said it wasn't really hard, but of course you had to understand how to use this stuff. The efficient normalization, this is also what we expected. There was very little code. You had to write code for normalizing a matrix, and you had to figure out how to do that. And maybe let me very briefly show that to you. So the solution, it's now past the deadline, so it's linked here. Here's the master solution. This was basically all stuff that was given to you. Let's look at the routine for here, for L1 normalize. So that's now the solution. Most of it is just doc tests here. We give you a lot of doc tests. And this is the code. And this is very, very typical for linear algebra in general. And in particular, if you do it in NumPy, SciPy, here you compute the sum of each row or column, depending on what you specify here. I won't go into any details. And here you do the multiplication so that everything gets normalized. So it's like 3 lines of code. You could do it in 1 line. Look at it. It's very typical. Of course, you have to know how it works. You don't even need to know special commands here, and then you can do it in. And of course, it's super important if you would have done this with for loops. I think I said it, but many of you also realized it while working on the sheet. These matrices internally in NumPy, they are implemented in an efficient way if you do these operations, but when you now go over this with a Python for loop, then it's super duper inefficient. You shouldn't do that. You should do everything with linear algebra operations. And that was also one purpose of the exercise sheet, to make that experience. I found it difficult to find the right NumPy functions. If I ever had a friendship with SciPy and NumPy, it is over now. That was, yeah. So remember, there is, I also said it in the lecture, there is a cheat sheet which we prepared for you, where we gathered, because NumPy, SciPy, it's everything linear algebra, and it's huge, so the documentation, it's huge, and it may be hard to find what you need. So here we have what you typically need for the purposes of this lecture, very nicely explained. So this is on our wiki. I said it already in the last lecture. In case you missed it, now I said it again. So that should be helpful. And in particular, everything you need for the lecture should be there. The exam, it's on February 28th, Tuesday, the usual day, but not the usual time. It's at 11. We don't know yet, 2 hours, 2.5 hours. We will tell you that in time. It's in this room, and the one below, it will be announced in time in which room you sit. As usual, in the last lecture, I will spend half an hour, little more, talking about the exam, doing some exam tasks together with you, telling you what are typical exam questions and so on. And very, very important, because this is a hard deadline and our Prüfungsamt does not accept late registrations. It's January 15th, so that's, I think, Sunday midnight. So if you want to write the exam, you should register. And I've seen it, many people have already registered. But yeah, so don't forget this deadline, please. So that's it for the organizational part. So let's start with the contents, which is really, really nice and exciting. It's about latent semantic indexing. Funny name, we will see what it means. So this is our matrix which we already used in the last lecture. And let's try to understand this a little bit better, because there's a reason I chose this matrix, which we didn't really need that in the last lecture, now we need it. There are these two words here, internet and web, which for the purpose of this example mean the same thing. You have that pretty frequently in language, two words which more or less in a certain context mean the same thing. You have a word surfing, which can mean different things in different contexts, surfing the web, surfing the beach. And now I have 6 documents. 3 of them, D1, D2, D3, are about web surfing, just using different words. Here it uses internet, web, here only internet, here web. D5 and D6 are about surfing the beach, and D4 is kind of about both. So that's the purpose of this example, easy to understand, of this toy collection. And now let's see what the problem is with the approach, how we did it so far. So this is just introduction, very easy to understand. Then we come to the mathematics. So let's, here we have a query, and it's a query about web surfing. So if you would now do an evaluation like we did it before, then we would say first document is certainly relevant, right? That's about what it has the word internet, web surfing. Second document is also relevant. It doesn't use web, it uses internet surfing, but it's relevant. This one is relevant. The fourth one is maybe a little bit less relevant. It's about web surfing, also about beach surfing. And these here are not relevant. They are about some other surfing. And now let's look at scores, how we computed them in the, let's maybe take wonderful orange here. So if we just take dot product similarity, you tell me between this vector and this vector of each of the 6, what do we get? For the first one, what's the dot product dot product? Just this vector times this vector. It's a number. 2, yeah, that's 2. Here, 1. Here, here, 3, 1, 1. Yeah. So if you would rank according to this, so we see here a problem. And the problem is, so these 4 are relevant and they get pretty good scores, except this one, right? So this one here is kind of, let me do it like this. Oh, this is 2, it's a bit hard to write at the bottom here. Too low. This is too low, and it's easy to understand. I mean, this is a relevant document, but the score doesn't reflect it. It just gets the same score as these not relevant documents. And why? Because it doesn't contain the word web. It contains the word internet, right? So it contains a different word meaning the same thing. And this is very deep down, it's a very deep problem with search. So how do we solve that? Here's a very simple conceptual solution. You just fill in the gaps. You say, yeah, in document 2, it contains just internet. It should also contain web because it means the same thing. And vice versa for D3, I just fill in the missing word. So what do I... now let's do the same thing. Let's do dot product similarity now. So now what we get, here we get 2. Here we also get 2. The first 3 documents are now exactly the same, right? Here we get 3, here we get 1, and here we get 1. And let me maybe also write again the... So this one is relevant, this one is relevant. So now the scores reflect the relevance. So if we just knew how to, and this is not relevant, and this is not relevant. So now by adding the synonyms to the documents, we somehow made it work. And now the goal of what we are doing today is to do this auto-magically. So fully automatically, not by some dictionary or someone telling us these words are the same thing, but just from the matrix. So in learning, you would say unsupervised. And how do we do that? This miracle, we will now make it happen. So here's a simple but powerful observation. If you look at this matrix, where we now changed what we would like to have, if you look at this matrix, this has rank 2 and column rank 2. And what does column rank mean? It means, now this is linear algebra, there are 2 vectors, and I wrote them here on the right side so that you can express each document on the left side as a linear combination of the 2 things on the right side. And let me just do that. So the D1 is actually just, this is just B1, right? It's just B1. D2 and D3 is also just B1. D3 is also B1. What is D4 expressed as a linear combination of B1 and B2? Yeah, it's just the sum of the 2, and that's a linear combination. So in this case, the linear combinations are really simple. It could be 0.2 times 1 plus 0.7 times the others, but it's just a simple example, and here it's just, yeah. So now we have proven that this matrix has column rank at most 2, and it has column rank 2 because, for example, the first one and the sixth one are linearly independent. One is not a multiple of the others. So what we have here is a low rank matrix. And if you look at the matrix on the previous slide, if you would compute the rank, it's a full rank matrix. And full rank means the rank is 4. The rank cannot be 6. You have a question or comment? Oh yes, thank you very much. This matrix here has rank 4, and we will compute it, and then in a second we will do some coding, and we can just compute the rank with NumPy. So yes. And one important linear algebra fact, we will do a lot of simple linear algebra, and some things I will just mention and not prove. So this year, the original matrix had column rank 4. This matrix can never have column rank 6. Why is that? Because the column rank and the row rank is the same. That's not trivial to prove, and it looks a bit magic, like so many things in linear algebra. I mean, what do the rows, if you just look at the row vectors, that's vectors in a six-dimensional space, what do they have to do with the column vector? It looks like nothing. But it's a fact that you can have at most, so in this case you have 4 linear independent column vectors, and this you can prove, then you also have 4 linearly independent row vectors. So the column rank and the row rank is the same, which is why one can speak of the rank of a matrix. If they would be different, you would have to say which rank, column or row. But you can just say column or row. Is it too loud? Yeah, okay, thank you. And we can make this a little more precise, what I wrote here, I can have two vectors, and each vector is a linear combination of the two. This is exactly what matrix multiplication does. And let's understand for a moment how matrix multiplication works. I think you all know how matrix multiplication works, but for the purpose of this lecture, it's also important to understand how it works in the context of something which is real, like documents. So for example, I mean, that's always the hard part, understanding mathematics in terms of the real world. So if you just look at, so this is, I'm saying that this matrix product, and let's first maybe verify that this is a 4 times 2 matrix here. Maybe let's do that in orange too. Whenever you do a matrix multiplication, you should always check that the dimensions work out. This is a 4 times 2 matrix. These are just headings. This is a 2 times 6 matrix. And this is a 4 times our original matrix 6, not the original one, the changed one. So this works. 4 times 2 and 2 times 6. This has to work. Otherwise, can't multiply them. Gives a 4 times 6 matrix. And how does matrix multiplication work? Let's just produce these 4 entries and see how it works. And I do that slowly, just in case you forgot how it works. Let's maybe do this in green first. So what I could do here, I could take this 1, 0, and then multiply it with 1, 1. So I take, it's all dot products. You take rows of this matrix and take the dot product with a column of this matrix. So it's 1, 0 times 1, 1. It's 1 times 1 plus 0 times 1. And this gives this 1. So this is how this one originates. So, and let me do it just for all 4 so that it's clear. This is 1, 0 times 1, 1, and this gives this 1. And then let's see whether we find so many different colors. This is 1, 1 times 1, 1. It gives this 2 dot product. And the last one, yeah, which maybe let's take it in orange here. This 0, 1 times 1, 1 gives this 1. And also note the following property. So everybody, I think, can do matrix multiplication, but some things are then not so obvious. The effect of this 1, 1, by what I just did, is really to take this plus this, right? Which is what I told you earlier. If you look at it slowly, then this is, so this is really B1 plus B2. 1 times B1 plus 1 times B2. And this is exactly this one and this one. This is just the effect of the matrix multiplication, right? This column is just this times B1 plus this times B2. Yeah, and this is what I wrote here. And kind of, if you want to interpret this, then you could say, these here are here I have a collection of many documents. Here it's just 6. I just have 2 different concepts. And if you now go back to the terms, then this B1 is kind of the web surfing concept, and this is the beach surfing concept, right? And now each document is just a linear combination of the 2. And which linear combination? This matrix tells you. D1, D2, D3 are just B1, it's just web surfing. D4 is both, and D5 is just the second one. So that's just understanding matrix multiplication in terms of documents and terms. Okay. Now, what's the goal of latent semantic indexing? The goal is to somehow get this matrix automatically, and what I've told you so far already gives you a hint. The original matrix has rank 4, and this matrix has rank 2, and it's good that it has rank 2, because then we can express everything as a combination of few concepts. And the idea is that the high rank of the original matrix was actually not so much information, but more noise. For the purposes of search, we didn't really care whether web or internet was used. We kind of want to get rid of that noise. It's good to have lower dimension. And that's a trick, by the way, which is also very fundamental to many learning methods. And this is what LSI does. So you have a term document matrix, any matrix now, and now you have a lower rank, for example 2. So our rank here originally was 4, and now we have a 2. And now you want to find a matrix of the smaller rank which is as similar to the original matrix as possible. This is what we did here. We just had a rank 4 matrix, we changed these 2 entries to ones, and then we had a rank 2 matrix. So make as little change as possible to the original matrix so that we have a matrix of smaller and in reality much smaller rank. Maybe in reality you have a 10,000 times 1 million, you have rank 10,000, and now you want to reduce it to rank 100. You want to change as little as possible. Now we have to make it mathematically precise, what it means to make it as similar as possible, and we do that by subtracting the 2 matrices. If we would subtract these 2 matrices from each other, all that would remain is the ones here, and the rest would be 0. And now we have a matrix with small entries. We take a norm. The norm we take here is the Frobenius norm, which is just, so you take the difference, and then you take the squares of all the differences, you sum them up, and you take the square root, and you wonder why that norm, why not just the absolute of all difference summed up? And the answer is very simple. It's purely that way the mathematics works out. And that's very often the reason why in computer science you use a particular approach, because if you use that, then you can do mathematics, otherwise you can't. And we will see that in the upcoming lectures too. So you just take this norm, but it's not really important for now. What is important is you want to find a matrix of small rank that's close to the original matrix. So how do we get such a matrix? And is there any question so far, or was everything clear so far? This was the motivation. Yes, please.
I have another question, because you said why we're using this norm, and if I remember right my stochastics course, then it could also imply that the noise is normal distributed. Is this also a reason? Because of this Residian progress that we say we have normal distributed noise.
Yeah, this is exactly right. So there is, when you see something like this, there's always a relation to Gaussian noise. So in a sense, this method is optimal if you have a process like you have a real matrix, like what you actually have in the beginning when the world was created, and then some noise was added by a Gaussian process. So, and the Gaussian process, Gaussischer Prozess, you would now have to define what it means for a matrix, and this would now add noise to everything, and now you want to remove that noise again. And then this would also be the optimal method. So yeah, that's correct. We don't need that property, but yes. So how do we compute this approximation? And now a very, very beautiful mathematical construct, and I will tell you a lot more about it in the second and third part. It's the singular value decomposition. Oh, there's a question in the... Yeah, does it make a lot of documents equal? I mean, in the example, I just had 2 concepts. If you do it in practice, you have 100 concepts, and you don't have... A linear combination is also 0.1 times the 1 concept plus 0.2. So it will not happen that they are exactly the same. This just happens in my toy example. On the slide it was said factorization. Is there always a factorization? Yes, this is exactly what the singular value decomposition is about. The singular value decomposition is a very particular factorization, and we will talk about it now. It's a magical thing for any matrix, and that's quite popular exam question. Does it exist for any? It's for any matrix. Anything can also have negative entries or whatever of particular rank. You have 3 matrices so that you can write that matrix, and it's also not a square matrix or anything, any matrix. Really any matrix, so that you can write A as the product of 3 matrices. And right now we have no idea why 3 and why is that good. Where the 3 matrices have the following properties. U is an M times R matrix. And let's just write down the dimensions as I introduce you personally to these matrices. So this here is my original matrix. It's M times N. So U is M times R. R is the rank. The next one is S. That's a diagonal matrix. So entries only on the diagonal. The rest is 0. R times R. And then we have another matrix V, which is R times N. And now that's what you should always do when you multiply matrices. Check the dimensions that they match. M times R, R times R. So this gives an M times R. You can multiply it with R times N, gives M times N. So this works out. And now each of these 3 matrices has special properties. S is, as I said, diagonal. And U and V have this property, that if you take the transpose times the matrix, or here the other way around, you get the identity matrix. And I will show you on the next slide what that means, because it's very important, and then I will show you an example. And moreover, this decomposition is unique. Now, matrix multiplications can never be completely unique. And why is that? That's easy to understand, I think, in our example. Look, I could just switch B1 and B2 and switch these 2 rows, and I will get exactly the same result. If you can just switch B1 and B2 and the 2 rows here, I get the same result. And I can, if you have a bigger matrices, you can just permute the columns here and permute the rows in the same way, you get the same result. So it can never be unique, can only be unique up to permutation. But here there's a way to make it unique, namely these diagonal entries, you sort them in a particular way. We will see it in a second. They are positive. You can make it so that they are positive, and then you sort them. So largest first. I should maybe write that. Largest first. Writing down here is always a bit hard. And I think before I go on, I will show you an example. Largest first. Let's first see an example of this, just so that you have seen an example, and then we go back and forth from the slide. What I've already done for you, I've just copied the code from the last lecture. 1-to-1, the only thing I did, this was called inverted index.py, I called it lsi.py. Apart from that, it's exactly the code from our last lecture. And let me just run it. What it did was, okay, I have to call it, I had this, let's also recall our example 2. Let's make this a little, this was exactly the collection which we used, and now it will just show me the term document matrix. This is exactly the matrix from the slides, the original matrix. And then last time we just did some dot products, right? Just for this query, which is also the query this lecture. These are the... And now let's just do some, and that's actually super simple. Let's not do any... Let's just compute the SVD and show it That's actually pretty simple. It's USV is NumPy. Then there's a linalg submodule, SVD. Couldn't be much simpler. A. And now let's just print it, print U, print S, and print V. And you might find this, you don't need it for the exercise sheet, but you might find it helpful to play around with it a little bit to understand this. So let's also, so this is USV from the SVD of A. And let's also do an empty line here so that it looks nicer. And let's maybe, not maybe, but write, because these matrices now will not be purely integers, so let's write 1 digit after the dot. And let's maybe for now add another new line here so that they are not also, So now I have 3 matrices. I have this matrix, I have this matrix. So here you see Python actually, or NumPy, gives me just the diagonal entries. This is just the diagonal entries, and I can actually show you the whole matrix. Let's just do that. And I think it's diag S. And we will make the check that this is actually the thing. We will multiply them again. And let me actually check. Let me do that. And then let's look, check that U times S times V is indeed A. I can just, I just do U, matrix product with this, matrix product with this. I did something wrong. Yes, that's you might notice, and I have a slide later about this, Python gives me something slightly different than what I had on the slide. What I had, this is a 4 times 6 matrix. On the slide it said this should be a 4 times 4 matrix, rank, number of rows times rank. This is 4 times 4, rank times rank. And this should be now 4 times 6, but it's 6 times 6. And actually these 2 rows here, I don't want them. And I will tell you later why they are there. And I can just cut off these last 2 rows. I just take the first 4, where 4 is the rank rows. You do it in Python, that's super nice. You can just do it like this. This just says first 4 rows, 0, 1, 2, 3, not including this one, and this just means all rows. Oh yeah, you have to absolutely say that this is, yes, and now let's, yes, and let's maybe add a new line at the end here. And right now it's completely okay to wonder, what are we doing here? Why are these matrices interesting? I mean, yeah, and let me also write on top that we are, check that compute U times S and check that it's A again. So I have my, sorry, here's one more. So I have my original matrix A, so dot 0, but it's actually all integers. Now I have 3 matrices here, U, S, V. S is diagonal. If I multiply them together, I get, this looks like the original matrix, minus 0.00. Why minus point? Because if I would print it out, it would be minus 0.00002, because the method to compute this is a numeric method which only computes an approximation. So there will be small rounding errors. So now, what's special about U and V? Well, if let's maybe check that U transposed U is the identity matrix. This was one claim on the, and this is a pretty magical property. Let's compute U transpose times U. So you multiply the transpose of U with itself. And let's see whether I get the dot product with U. And let's see what that means. Yeah. See, I multiply the transpose of U. I mean, it's a square matrix, so I can do that. And now I get 1, 1, 1, and the rest is 0 or almost 0. If I do the same thing with V, let's do the same thing with V, except that I do now V times the transpose of V. I also get an identity matrix. So these matrices have a very particular property, and let's look at that property. So what does this mean? And I have some, and it means the following, and that's important to understand. If you, so how do I do this? So if I have my matrix U here, and if I look at the columns, let's look at the columns. And how do I do that? Which color? It has, it's an M times R matrix, right? M times R, so M terms, R columns, which means, let me write it symbolically like this. So it has these R columns. So this is 1, 2, R columns. So what happens if I multiply U transpose times U? If I do that, so this is now an R times M matrix, and this is an M times R matrix. So if I transpose it, then so this is now, my columns now become rows. And then I have U again, I multiply it with U, and now here it's like in the original. So so this is now 1, 2, R, 1, 2, R, and this is now this matrix. It's the identity matrix. So everything here is 0. And what does that mean? So what I'm doing for every entry here, for example, let's just take as usual in matrix multiplication, if I take the second entry and this one, then I get this entry here. So this here is just the product of the second one with itself, the second column with itself. If you compute the product of something with itself, it's just the norm, right? Let's also do that. If I have a vector x1, xn, and I multiply it with itself, but what do I get? I get a scalar, and that scalar is just the sum of the squares. And this is 1 according to this equation, which means this is the L2 norm of this vector is 1. So this diagonal means that all the things multiplied with themselves are all 1, they are all normalized. And the others mean if I multiply 2 with 3 or 2 with 4 or 1 with 1, and these are the same vectors, just here they are as rows and here as columns, then it's 0, and 0 means they are orthogonal. So what this means, ut times u equals the identity matrix, means what's written here, the columns of U are all L2 normalized and pairwise orthogonal to each other. So U is a very special matrix. And the same for V times V transpose. Now it means the rows of V are normalized, so each row has norm 1 and pairwise orthogonal to each other. So if you look at the matrix here, so this, if you just take the 4 column vectors here, I take any product, this times this, or first times 4, it's 0. They are all orthogonal. And the norm, that's why you have these not so nice numbers, will be 1. If you take the sum of the squares, it's 1. And what's the row? Here for you, it's the columns, and here it will be the rows. So that's the property of the singular. It's still not clear why this is useful, but now it's at least clear that this is a very special decomposition, right? Do you have a question or no question? So this is a very special decomposition. I have these, and it's also very important to understand, and you have to do this for yourself, ut times u is not the same as u times u transpose. You can also compute u times u transpose, but that's a completely different matrix with completely different properties. And if you think about it, I leave that as an exercise. This cannot be the identity in general, and also this. But this can, this, maybe let me write at least write this here. This is an M times R matrix, and this is an R times M matrix, which means this is now an M times M matrix. And I mean, if M is greater than R, it just can't be the identity, then it would have rank M, which is not possible. And here it's an N times R and an R times N. So if you do it the other way around, it's something completely different. Okay, but that was just for some, yeah? Yeah.
The identity that we have a lower rank than the full rank.
Can you say that again?
You just said that R is smaller than M, and where did we define it? Because we could write down in U as V for the identity. That would be.
The rank is always smaller than the minimum of M and N. I mean, if I have an M times N matrix, the rank can be at most the number of columns or at most the number of rows, because of what I said earlier.
If we had an N times N matrix.
Oh, it could happen. Yes, it can happen. That's completely correct. By some magic, it could happen if it would be a square matrix that this is also the identity. But then then you would have a very special matrix. So it's exactly right. So my statement was, in general, this cannot be the identity, but it could be in very special cases. You are completely right, and here also. Yes, but in general, this is not the identity, and when M is greater than R, it can't be the identity, and when N is greater than R, it can't be the identity. So these are all these small puzzles or things to think about. And now, the magical thing is, if you have the singular value decomposition, which here we just take for granted, in the exercise sheet you will compute it by hand, then we can do the following. So now we say, okay, we have our A, it's rank 4, we now want a rank 2 matrix, which is very close, where you wonder, how do you do that? Now you just take, and let's just do that let me first show it and then do it in Python. Just take the first k columns of U, so the first 2 in this case. Just take the first 2 diagonal values of S, they are sorted by size, so the 2 largest, and take the first 2 rows of V. And now, as I told you, U, the columns are pairwise orthogonal and normalized. If I take a subset, they are still pairwise orthogonal and normalized, right? I'm just taking something away. And the S is still a diagonal. And now I take this matrix, and let me just write the dimensions here. So what do I have here? This is, this UK is now, it's still M times, but it's now not the rank here, but it's K. This is K times K. and this is k times n. So the product is again, it's just the same dimensions as my original matrix. And now this matrix has exactly this magical property. It's a matrix of lower rank, which is as close to this Frobenius norm to the original matrix as it possibly can. And let's just do that and see what comes out. So let me just remove these checks here. Oh, what did I do? This was just for checking some stuff. And now let's compute the rank 2 approximation. So what I do now is I take the first k columns from U. So let's just, let's make it a variable here. UK is U. So I want all the rows. Let me just write it like this so that everything will be aligned. And now I take the first k columns. For S, it's a diagonal matrix, so I take the upper kk portion. So I will do it like this. And let me put a space here, or maybe not. 0k, don't know what's the... And for, no, let me write like this. For V, I will just take, the first k rows. And as I showed you on the, so this should work now. And now I just take the product of these. So I take UK times SK times VK dot. I should use dot to do matrix multiplication. Let's first check that it works. Yes, it works. And now let's just print it. This is now the rank approximation, and this should be best rank k approximation. And now I do print it and maybe print a new line afterwards, and I don't print anything else. Let's see. So now we have just done what I've said on the slides, and what happens? Look at the original matrix, and what did I get here? So it's not quite how I did it manually. When I did it manually, I actually put a 1 here and these became all equal, but it did something similar, right? So this vector now becomes 0, 9, and this also answers the question from the chat. So it's not like in my toy example where everything became perfectly just one of two concepts. Now this first one, 1, 1, 0, became 0, 9, 0, 9, 1, 1, 0, 1, so it didn't change it much. This one, 1, 0, 1, 0, the 1 became a little less, but the 0 now became a 0.6. So it kind of did figure out that web and internet are the same thing. It made these entries the same. The 1 didn't change much, gave me a little bit of beach here for whatever reason. Here it did the same thing. So it just, here it added the 0.6. This became a little less. Didn't change this one much, and it didn't change these at all. So somehow, and by what I told you so far, at least you have some intuition of why it did it, right? It just says, okay, let me try to do something rank 2 that is as close as possible to the original matrix. And by what and apparently what I did, just a second, what I did was not the best in Frobenius norm, otherwise it would have found it. So in Frobenius norm, this is actually closer to this matrix than if I just replace these here by 1. Yes, please?
I have a question.
Mm-hmm.
Now we took the first entries of the middle matrix, it was called S.
S, 3, 8 and 1, 5, right?
And it's sorted. And do I understand it right that it's important that it's sorted and we take the highest values and let's say something like this is the highest significant
Absolutely.
dimensions or differences we take and we ignore the not so
Yeah, now you are asking already about the mathematics, and we will come to that in the next part. Why? But it's exactly like you said, like this is doing like a component analysis sort of the matrix, and this is the most important component with a weight of 3.8. Next important with 1.5. So if you've heard of principal component analysis, this all has something to do with eigenvectors and this is less important, and this is even less important. So that's why it would not work if I would take any two. I have to take the two with the largest value, absolutely. And it has something to do with important directions or important components of the original matrix. Yes. So that's and the proof. But let me just say that one thing again. You may wonder, why didn't it do this nice fill-in 1, 1 here? Because Frobenius norm-wise, that would be worse. So if we would compute the Frobenius, you can compute the Frobenius norm actually. If you do 1, 1, you take the difference, then you have a matrix with 2 1s here, and the rest is 0. If you sum up the squares, you have 2. You take the square root of 2. So this here will have a Frobenius norm less than square root of 2. And this SVD is just doing the mathematically optimal thing. But it's pretty good. And I will show you at the end of today's lecture or next lecture, when you do that in practice, it actually does something nice. I think it's time for a break now. You can think about more questions, and then you have a question now? Yes, please.
Yes, I'm unsure if you said it, but I didn't hear it. The V matrix, you said that for some reason it had extra rows or columns that were just sorted away, and you said you would get back to that later. Are you going to do that?
Absolutely, I will get back to that after the break. Yes. Okay, let's have a 5-minute break and maybe get in some air, and then we continue. So we're ready to continue. And since the exercise sheet will be mathematical, I will now give you mathematics background and also a bit calculation background. So how does one compute the SVD? Do we have mathematics students in the room? Ah, great. So you probably know about the SVD, or at least, but have you ever computed one by hand? Probably not, right? So you will do that for the exercise sheet. So computing the SVD. So mathematically, you can compute it from the eigenvalue decomposition, or just eigen decomposition. And I will show you how to compute. So eigenvalues, eigenvectors are more familiar to singular vectors. You probably haven't heard it before unless you study mathematics. In practice, what we just saw in the code, you use numerical methods, which means iterative methods, which then stop after a time and have to compute some approximation. Just very quickly, I will not go, this is not a numeric lecture. If you only want the largest eigenvalues and the eigenvectors that pertain to those, you use a method called Langzos. And it has the nice property, so I only want the top k eigenvalues, eigenvectors, singular vectors. It has complexity k times the number of non-zero values in my original matrix. So that's kind of the best one can hope for. And of course, in typical term document matrices, most entries are 0. So if you would use what I used now for the toy example, I have a slide about this, won't work. For a dense matrix, this takes a very long time. And I will also mention about SciPy. So let's first compute it mathematically. Let's go back one step, eigenvalue decomposition or eigendecomposition. And I just call it, it's not actually called EVD in the literature, but I just call it like this so that it's similar to SVD. So, and let's just look at real symmetric matrices. And I will give you an example in a second, and maybe that second is now. Let me just call it B, why not? Let's just take any matrix that comes to my mind, and the matrix that comes to my mind right now. Let's take a 2, let's take 2, 5, 5, 2. So this matrix has real values. It's symmetric, which means when you transpose it, I mean it's symmetric. You can mirror it across the diagonal, it will be the same, which means you take the transpose, it's still the same. And then this has n, so in this case 2, so this is a 2 by 2 matrix. Let me always write this down here. So it has 2 eigenvectors which are orthogonal to each other. And how do you compute them? Well, maybe who sees an eigenvector here? If you know what an eigenvector is, you see it immediately. If you don't know it, you will see in a second what one is. Who sees what? An eigenvector. What's the eigenvector you see immediately here if you know what an eigenvector is? So one eigenvector which you see immediately if you know what an eigenvector is u1 equals 1, 1. And why is that an eigenvector? That's an eigenvector, I mean the definition is written above, if you multiply the matrix with the vector b times u1, and let's for once do it, let's just write it down in full, 2, 5, 2, 5 times 1, 1. What's the result? 7, 7, exactly. So of course you always get some vector, but this vector is special because it's just a multiple of the original vector, and that's very special. Most vectors will not have that property. You multiply it, so this is, if you view it geometrically, it's the linear transformation of my space. It will do something to my space, it will stretch it and change it. And here this vector is only stretched, but it remains, the direction remains. And this thing here, that's called, this is an eigenvalue. This is the eigenvalue of that eigenvector. So it eigenvalue 7. And that's the eigenvalue of that eigenvector. And now, if you have an eigenvalue, if you have eigenvectors, all but the last one, you know that they are orthogonal to each other. Now, there's only one vector left here. What's the vector, or a simple vector that's orthogonal to 1, 1? Yeah, minus 1, 1. Or 1 minus 1. Or, yeah, but let's take minus 1, 1. Minus 1, 1. That's orthogonal. So, and that's really magical. I mean, you don't see why that is, because it must be orthogonal, and there's only one vector here in 2, 2, which can be orthogonal to this one. This is also an eigenvector. It just will be, I know it, which is not obvious. Why should the orthogonal vector to that one also have the property that when I multiply it by b, it's a multiple of itself? Eigenvectors are truly miraculous. And they have very, very deep meaning for our world. So all of quantum physics is about eigenvectors, eigenvalues, as you might know. So what's the result here? Hmm? 3, I hear a 3, yes. And the other one? Minus 3. So it's also a multiple, right? And in this case, it's minus 3 times u2. So as you can see, and maybe I should rewrite this because I was a little bit generous with this space here. So this is, yeah, this is eigenvalue 7. And this is now eigenvalue minus 3, and I chose that example. So eigenvalues can also be negative, right? They don't have to be positive. So now you wonder, why are my singular values always positive? We will get to that. Eigenvalue minus 3. So now I have this pair of oh, and actually, okay, let's normalize what's the normalized version of, let's maybe do that here, normalized versions of U1 and U2. I mean, what should be obvious is if I take a multiple of this, I multiply with any constants, it's still an eigenvector, right? Because everything is linear. If I take 2, 2, I would get 14, 14 here. What's the normalized version, L2 normalized of U1? So let me write it like this. So I think it's 1 over square root of 2, 1, 1. And yeah, 1 over square root of 2 squared is 1 over 2 plus 1 over square root of root square. 1 over 2 plus 1 over 2 is 1. If I do it for 2, it's the same but just with a minus sign. And minus 1, 1. So these are the, yeah. Okay. And now, by these properties, this holds. I can write now B as, and this just follows from what I just did. It may not be completely obvious, but you could compute it, which means that my B, which is 2, 5, 5, 2, that's my B. And I can write it as, I now define a matrix U, and U is just a matrix where I put the 2 eigenvectors side by side, the normalized ones side by side, and that's now just as columns U times, and I put the, I could also put S is now just, maybe I should give these 2 eigenvalues a name. Let me call them lambda 1, and you usually call them lambda. So this is eigenvalue lambda 1, 7, lambda 2, minus 3. So now I have a diagonal matrix which has, well, let me just call it lambda 1 and lambda 7, lambda 2, 0, 0, lambda 2, and then the transpose of it. So it's U times S times UT. So difference to the singular value decomposition is the matrix on the right and on the left is the same. So this is equal to 1 over square root of 2. And now I write these 2 vectors here, minus 1, 1, times, and now the diagonal matrix, 7, 0, 0, 3. And now again, the transpose, the factor is not touched by the transpose. Now I transpose it, means the row here becomes the column, and like this. Minus? Oh yeah, absolutely. Minus 3, yes. This should be minus 3. Let me make it absolutely. Mm-hmm. Yeah, I was just trying to do the proof in my head why. I mean, this here, that you can write it like this, follows from the eigenvalue, eigenvector properties, but I don't have a one-sentence explanation now, doesn't matter. You have this now, you need to do the exact same thing for the exercise sheet, so it's good that you have it. So now we can do something like this for symmetric matrices. You can just compute eigenvectors, you can guess one, you can compute the others, and for the matrix, let me quickly show you the exercise sheet, which is a very, so where is it? It's not, oh here it is, yeah. So that's the matrix you have. It doesn't look so easy, right? It's a 3 times 5 matrix, and you should compute the singular value decomposition by hand. But it's a rectangular matrix. So now I showed you how to compute stuff if you have a symmetric quadratic matrix. Well, that's okay, first one thing. Okay, I was a bit too fast. Here, I told you I see one eigenvector. Actually, why do I see it? I mean, if you see these values here, 1, 1 is always an eigenvector because of the symmetry. So that was easy. Let's say you don't see it. How do you compute it? Well, you can always compute it via the determinant. And let's prove that this is correct. Why are the eigenvalues zeros of, you take this matrix B minus, you consider lambda as a variable. So let me write that here. Lambda is the variable here. So this gives you a polynomial equation. And we will see it in an example. So what does it have to do with the determinant? Well, let's just look at, let lambda be an eigenvalue. That's actually easy to see that each eigenvalue is 0 of this function. Then we have some vector u, which is not 0, such that b times u, we have an eigenvector, it's a definition of an eigenvalue, which if you multiply b with it, you get a multiple of u, and the factor is lambda. So let's just, so b times u is lambda times, and let's also write a matrix here, that's now the identity matrix, I, u, which means I can write it like this, b minus lambda times the identity times u is 0. And now I have a matrix times a vector which is not 0, is 0. And if a matrix sends a vector, a non-zero vector to 0, this means the determinant of the matrix is 0. I won't prove that, but that's just how it is. So that means the determinant is, which means this matrix doesn't have full rank. That's also a magical thing of linear algebra, these determinants and what they have to do with not having full rank and so on. But this is stuff which you do in the linear algebra lecture. Okay. So this is just the proof. So this might look intimidating, but it actually follows directly from the definition of, it's just lambda times, has something to do with eigenvectors. So let's just do it for our example matrix. So we have B was 2, 5, 5, 2. And now let's just do B minus lambda times the identity. Well, that's just subtracting lambda from each diagonal element. 2 minus lambda, 5, 2 minus lambda. And now let's just compute the determinant of that. Determinant of a 2 times 2 matrix is not very hard. Determinant of large matrices is no fun. But by some magic, the determinant of which you get when you do the exercise sheet, they will also be nice. You don't have to compute ugly determinants. So what's the determinant of this one? Who can tell me or write in the chat what the determinant is? Determinant of a 2 times 2 matrix? So you... 2 minus lambda square minus 5 times 5 square, exactly. And let's compute that. That's lambda squared, right? Minus, what do we have here? 4, here's a 4, minus 25, which means we have minus 21 in the end, right? And then we have minus 4 lambda, right? Is that correct? I think it is, yeah. And now we can find the zeros. Of course, there's a formula for that, but I mean, to find this, let me show you this tree. It's a little bit sheaf. I'm not happy, but I won't write it again. I'm unhappy that it's not completely horizontal. Okay, so if you have two zeros, I mean, if you have if P and Q are zeros, and then you would have lambda minus P times lambda minus Q. So if I just compute this, I get lambda square minus P plus Q plus P times Q. Yeah? So I have, just by, if you have these integer numbers, you can usually see the zeros by looking at it. I have to find two numbers so that the product is 21 and the sum is 4. Two numbers where the product is, so find, so no PQ formula, so find PQ, let me just write it, such that P times Q is minus 21 and P plus Q, and there's a minus here, is 4. And the two numbers are 3 and minus 7. Almost, right? 3 plus minus 7 is minus 4. Mm-hmm. Yeah, it's 7 and minus 3. And of course, you could have cheated because these are our eigenvalues from the previous slide, right? So this actually, so the determinant is, yeah, let's just continue here. This is just lambda minus 7 times lambda plus 3, right? So, yeah, so the two eigenvalues are. Say it again. There's a lambda missing on, oh yeah, yeah, absolutely, thank you. That's unforgivable. Plus P times Q. So very often you can, in case you didn't know that trick, that's if you are given and you know that there are nice solutions, you can always see them like this. You don't need the PQ formula. I mean, that would give the, yeah, these are our, yeah, our two eigenvalues. And now from that you can, but I don't think I will do that. I mean, now you can compute the eigenvectors from these two by solving a system of linear equation. But this you can figure out. Let's maybe continue because there's more interesting stuff. So now we know how to compute either by divine intervention or by computing the determinant eigenvalues and eigenvectors for a square matrix, but we want singular values. Okay, here's one more thing. I'm again ahead. Let's assume our matrix has a rank and the rank may be smaller. Okay, this is something I wanted to show you. It's again basic linear algebra calculation stuff. So let's assume my B, how do I write this? My B is an n times n matrix. Yeah, and I want to take time so that you understand it. And let's assume, so this I can write as Let me write, so I have a U, I have a S, and I have the U transpose. So this is now, this is my U, this is my S, and this is my U transpose, and they are N times N, and this is N times N, and this is N times N. So that's quite simple. And now let's assume R. For the picture, let's take a smaller rank. Let's assume, just so that the picture is interesting. So R is somehow smaller than R. So then I have 0 eigenvectors. So then my matrix will actually look like this. So I have, so this is R now. And here I have some interesting values, and here I will have 0. So this part of the matrix is 0. I mean, off diagonal, everything is 0 anyway. Let's maybe write the R inside here. So this is R and this is R. So here I have zeros, here I have zeros. Everything off diagonal is 0. But the lower, on the far end of the diagonal, they are also 0. So if I do, so if this is R here, and this is R here, and now I'm claiming these values, and that's now a visual proof, don't matter. Yeah, they will be multiplied by only zeros. If you don't believe it, you can try to prove it yourself. If I have something which is all 0 here, I mean, think about it. If I let me maybe take one, maybe a green thing here. If I do this line here and I now multiply it with this matrix, then it somehow gets here. So everything here will be multiplied by only, everything beyond the R will be multiplied by only 0, and the same thing happens on the other side. So this part, if in my diagonal matrix there are zeros, and maybe there are 3 zeros, then the last 3 columns of U and the last 3 rows of the transpose, I can just throw them away. It will make absolutely no difference. Which means what I can do, if the rank is smaller, oh, this curled up. Okay, I can write, and I can always do that, I can always write this N times N matrix as N times R, R times R, R times N. So I just omit the eigenvectors beyond. They exist because I always have N. I mean, these are the ones spanning the core of the, so all, it just spans the space that is sent to 0 by this linear map, but that's not important now, but I can just ignore them here. So I can just write N times R, R times R, R times N. And this answers the original question. So what I said earlier, what NumPy computes here, these 4, we haven't come to that yet, but these are also eigenvectors of some matrix. Which matrix we see in the beginning, and if so, the rows here are eigenvectors of some space, and there are just 4 of them, and it's 6-dimensional space, which means there are 2 more eigenvectors. And NumPy just gives them to me in case I want them. I don't need them because they will be sent to 0 by a certain linear map, but it just gives them to me. But I don't need them, for the same reason that I can omit these things here.
I have a question.
Yes, please.
I'm not sure right now if I have to write an now we have some kind of a choice, which of the vectors we will take for our base, or
Which choice do we have? We don't have a choice. The eigenvalues are fixed, right? If I move all the eigenvalues can also be 0. And if I move all the eigenvalues which are 0 to the end, that's a well-defined number. Maybe one thing wasn't clear, and maybe then you ask your question again. The order of these things here must be the order of the eigenvalues, otherwise it doesn't work. Maybe that's something I didn't make clear. Yeah, is that maybe a problem? Here I can't just switch the two, then it's not correct. I mean, if I write here the first eigenvector and the second eigenvector, then the diagonal I must write the eigenvalues in this order, otherwise it doesn't work. So I wrote it implicitly here, but I didn't explain it properly. So I can't just permute them any way I want and I still get the same result. Does that answer your question?
I'm just thinking about, like, when we have something of not the full rank, then we have some kind of linear combination that, for example, if we take a 3 times 3 matrix, that the third of our vectors is a linear combination of the first 2 ones of them.
Yeah.
And now there is kind of an order because we can derive each of them by a pair of other 2s of them.
Yes.
And I just tried to understand, maybe my intuition for eigenvalues is a bit rusted because Math 2 is a bit ago.
Yeah.
I remember something like, hey, we have for each of our dimensions of our rank, we have one eigenvalue.
Yeah.
Now I'm a bit confused why they are fixed, but I think I have to look it up again.
Maybe part of the confusion is this B is not our term document matrix. So here it's not about vectors being linear combinations of others. We will now come to this on the next slide. I mean, we had a rectangular matrix, and here we are talking about symmetric square matrices. So I haven't told you yet how we get from our A to the B. And the B actually is something where you don't have that intuition, which we had earlier. So maybe let's go to that, and then maybe it will resolve. Or if not, maybe you just ask it again. So how do we get now from eigenvalue decomposition, which you will do for the exercise sheet, to singular value? And that's actually simple. Here is, I have now an arbitrary m times n matrix, and now how do I turn it into a square matrix? I just take A times A transpose. And that's super simple. Let me just do it for you. A times A transpose. I mean, why am I doing this? We will see in a second. This is now, and this matrix product doesn't have a good intuition, but it's certainly a square matrix. You can see it. It's an m times m matrix. And now, let's just take symmetric means the transpose is again the same matrix. If I take the transpose of this matrix, A times A transpose transpose. So in general, in case you didn't know this, in general, if you have two matrices, and this is something which is proved easily by just doing the basic math, the order changes, right? If you take the transpose. The transpose of a product is the product of the transpose, but with the factors switched, which means here I have A, T, T times A, and A transpose transpose is of course, like this, and A transpose transpose is just the original matrix. Yeah, so it's just you change the order and take the transpose, which means you get A transpose transpose and A transpose, and A transpose transpose just A. So yeah, symmetric. which means it's a symmetric matrix, which means this has a reduced eigenvalue decomposition within this one. And let's just, this is now, so this is now an M times M matrix, and it's symmetric. We have just proved this, which means we can find the non-zero eigenvalues. So if this has rank R, it has R non-zero eigenvalues. We take the R eigenvectors, write them as columns here, write them as rows here, and this is what we get. We get this decomposition. I can do the exact same thing. Yes, please.
I have a problem with your proof.
Yes?
Because we say it's M times N in dimension, and we say it's we don't. Okay, sorry. I just was thinking about the dimensions beforehand and thought about how our matrix is, but now I see my mistake.
Okay.
I thought the backside is N times N, and the water is N times N.
So this is M times N, right?
Yes, it's okay.
And then the transpose is the other way around. Rows become columns. You can do the same thing. Oh my. You can do the same thing with the other way around, AT times A. This is also symmetric, now N times N. You can just do the same thing. Now this is an N times N matrix. It's also symmetric, same proof. You also have, this also has rank R. It will also have R non-zero eigenvalues, so which means you can have, so these are now the eigenvectors of this funny matrix. These are R eigenvectors of this funny matrix. It's different eigenvectors. And now, by some magic, this already gives me everything for the singular value decomposition. It's actually easy to see. Let's assume, this is now not a complete proof, but almost complete. Let's assume that A, and let's just ignore the blue stuff for a second. Let's assume A is USV with the properties, and the properties are with the properties from the, with U times U is the identity matrix, S is a diagonal matrix, and V times Vt is also the identity matrix, right? So this is the SVD properties, and let's just do A times AT. A times AT is then, well, it's U times S times V. Now the transpose of everything, but with the order changed, which means it's V transpose times S times U transpose. S transpose, for a diagonal matrix. If you transpose a diagonal, nothing happens. S transpose is equal to S. I mean, you transpose around the diagonal. Well, and what do we have here? Here we have V times V transpose. This is exactly the identity matrix, which means it disappears. I have U times S, a diagonal matrix multiplied with itself. You just square the values on the diagonal. That's also easy to see, which means here you get U times S square times U transpose. Right, that's the usual linear algebra magic. You write something and then suddenly stuff disappears and you get nice expression. Let's also do it the other way around because it's so nice. Of course, you have to be careful that it's actually true what you're writing down. Now we are writing the transpose, which is Vt times S times Ut times A, which is U times S times V. Now here we have, and it's exactly what we need here. So this is now the identity, which means in the product we can drop it, and this is now Vt times S square times V. Yes, and this proves, so if something like this exists, and you can, by the same way you can, the eigenvalue decompositions give it to you, then U, the matrix U from the singular value decomposition is just the eigenvectors from this A times AT, and this is also how you do it for the exercise sheet. You just compute this matrix and compute its eigenvalues and eigenvectors, and then the V matrix, you just get it as the eigenvectors and eigenvalues from this matrix. And what this also shows is that the eigenvalues of this and the eigenvalues of this are actually the same. So what we, the singular, so the two matrices S1 and S2 from the previous slide are actually the same. This is also easy to see if you have a, let's say, it follows from this proof, but you can also prove it directly. Let me just write it here. Let U be an eigenvector of, let's say, A times AT, which means you have A times AT times U is lambda times U, right? Which means if you just multiply the whole thing by A transpose, you get A transpose times A times A transpose times U is equal to lambda times A transpose times U, because everything is linear. Now I have now I've constructed a vector here. I've done two things at the same time here. So now I have so ATU is now an eigenvector of this other matrix, right? With the same eigenvalue, which means if it's an eigenvalue for AAT, it's also an eigenvalue for ATA. Of course not with the, so this even gives you a transformation, how you get the eigenvectors from the one matrix for the other matrix. Actually, for the exercise sheet, you don't need to compute this one. It suffices to compute this one, and there's a trick to get the eigenvectors of this one. It's written on the exercise sheet. And I think it's very important to have an exercise for this where you actually compute this, because otherwise you just hear it, you may believe it or not, but you only really understand it when you do it, and when you do the calculations. And you just need everything what I explained to you here. And it's actually pretty nice to do it by hand with a small example. Yes?
Now I'm a bit confused why y times yt is the identity. That's the point I don't really...
Which one? This one?
This one, yes.
Oh, I assume that... So I'm assuming that I have an SVD for A. So this is the SVD of A, U times S times V. And the SVD has these properties, that U transpose U is the idea. Yeah? Okay. So if I have a singular value decomposition, which means here the columns are pairwise orthogonal, here the rows are pairwise orthogonal. And then, so from the singular value decomposition, I get eigenvalue decomposition of these two funny matrices. This is what I'm showing here, and it's also working the other way around, which I didn't really show. Okay, and now comes a lighter part, but first one more comment. Doing it in Python, I showed it to you. You can use NumPy linalg as SVD. That's for dense matrices. Everything in NumPy is for dense matrices. This will take forever on a large matrix. I mean, already for the last exercise sheet, if you would have used NumPy, would have taken forever. It's made for dense and not very large matrices. And also NumPy gives you the non-reduced form. I've already explained it to you. It gives you, we have learned now that these are actually the rows are eigenvectors of this AT times A matrix. Thank you very much. And it just gives you the two other eigenvectors which are actually mapped. They have eigenvalues 0, which means we don't need them. But since the method which NumPy uses computes them, it gives them to you, whether you need them or not. But we can just drop them. Yeah. And this is not part of the exercise sheet, but let me just tell it to you. There's in SciPy you have the same for sparse. It's not absolutely analogous. SciPy sparse linalg SVDS it's called. This is not using a particularly efficient algorithm. It used the Rayleigh-Ritz method, but I'm not talking about this here. You can check the documentation. Anyway, you don't need it for the exercise sheet. That will be non-coding. And maybe here's the time, before I go to the last, smaller part, why in the past we did coding exercises for this, which is very nice, because if you do this for a real document collection, then you actually see how just by linear algebra magic you find concepts, like you find real things in your data. And I will show it to you, I think, next lecture for an example collection. Right, these web surfing, beach surfing things, you actually find it, like you find underlying topics. Just by doing a singular value decomposition, you find topics in your text collection. And I mean, the algorithm just gets the numbers, doesn't know what the words mean or anything. And it's very nice to see that. But if you just implement this, then you can implement it without understanding anything, right? That's the problem. You just call SciPy parse linalg SVD, you do the matrix calculation, but you don't really understand how it works. That's why I think that a math sheet and one where you actually calculate, so let me go once more here. What you actually do is you take this particular matrix and you actually compute the singular value decomposition for this one, which means you compute A times AT, then you compute the eigenvalues and so on, and then you also check, are these really pairwise orthogonal columns? Are these really pairwise orthogonal rows? Is this a diagonal matrix? And I think it's a great way to learn it. So last part. It's not so long, so maybe we could make a break, but then maybe it takes too long. So how do I use it now for document retrieval? Let's just go, and that's now a little bit lighter again. I mean, this was the math, now it's again using it. Where was the whole point was this, right? Now I changed the matrix here in the beginning. I just did it by just adding these ones, and now I get better scores, right? I do the exact same thing. I do dot products with a changed matrix, and I get better scores. So that's the simple way. And this will be variant 1, which I will talk about in a second. Just replace your matrix with the new one with lower rank, and then just do the same thing as before. But as we will see, this has a pretty obvious problem. So here actually I did it. That's exactly the matrix, if you remember, which we get here. It doesn't do the 1-1 thing, because that's not optimal in the Frobenius norm. It does these funny numbers here. So why don't we just do this? We replace this by that, and now we do retrieval with this matrix. Do you see a problem? Yeah, it's not a sparse matrix anymore, and that's really a problem, right? If this is 10,000 times 1 million, now you have and this is what the linear algebra will do. It will not leave any non-zero value, because it's now doing, here actually that's a super coincidence for this toy example, but usually nothing will be, and that's written on the next slide. It's a dense matrix. All or almost all its entries will be non-zero. Here's just, so this is huge, right? Let's just say 1 million terms, 10 million documents. Now I have 10 tera. So if I have 8 bytes per entry, I would have 80 terabytes of data. You can forget it. So that's not practical. But what could we do? And this is also something for the exercise sheet. You will just do it by hand, all 3 variants, just to check that it really works, that the same thing comes out. Just do we'll just give you, that's the second exercise. You just get a query vector here, a very simple one, 1, 1, 1. This has 3 terms, this matrix, and now you just compute similarity scores according to the 3 variants, which I quickly explain now. So, this matrix here, this V matrix, in this simple example, where do we have... Okay, I haven't shown you the... No, it's just the first 2 rows here, right? If I take this here, this gives me these are exactly my concepts, how I started with, right? They now tell me for document 1, take minus 0.4 times concept 1 and minus 0.5 concept 2. Now it's not like 1, 0, 1, 0, 1, 1. It's a real linear combination, but this is what this matrix V gives me. So yeah, I've copied the value here. So instead of working with the original matrix, and maybe let me go back once more to make it absolutely clear. So in this case, instead of working, or I don't know which picture do I take. Instead of working with this matrix, I could just work with this matrix here. This is equivalent to this one if I know the concepts, right? Instead of this one, which is in 4-dimensional space, I could work with this one. It has the exact same information. And it's much simpler. It tells me these 3 are just concept number 1. This is concept 1 plus concept 2. So I could do that, and that's what I do for variant 2. But now I also have to map my query to the lower dimensional space. I mean, my query also has 4 dimensions. If I want a query on this matrix, I need a query in 2 dimensions. And just with a little bit of linear algebra, I can do that. Okay, it's much better now. Let's just skip this. So let's just do the matrix multiplication. Here's my query vector. This is just replacing my original matrix with my rank K approximation. So that's just the approximated dense matrix. This I don't want to compute directly. It's terrible because this is dense and very large. But how did I compute this? I computed it like this with these truncated USV matrices, first K columns, first K eigenvectors here, top K singular values, first K rows. Now let me change it a little bit. So now this product, which I would like to compute, is equal to this product. And here I have my VK, which means I could simply, if I get a query, I just compute this thing here, which gives me this, right? This is the same as this. This is just my QKT below. So I get a query, I multiply it by UK and then by SK, then I get a query which is now in, and let's maybe also check that. So that's a 1 times M vector. My original query was M times 1. This here is M times K. Oh, should do this in orange. This is 1 times M, M times K, K times K, which means here I get 1 time K vector, not plus, but times. Yeah. And I will skip these considerations on the runtime. So this is this is more meaningful now. I just can I just store this matrix here. So this is what I could do. I just store this matrix, and then when I get a query, I map it to from 4 to 2 dimensions by what I just showed you. And there's a last variant, and that's the last thing we do, and that's I can compute this matrix. And this is the matrix which I talked about earlier. If I do it the other way around, I get the identity matrix. If I do it this way around, I get a matrix which is not the identity matrix in general, but it's a matrix that has a very interesting property, and at least I wanted to briefly show it to you. One can prove with a little bit of linear algebra, which I will skip now, it's also not important for the sheet, that just by using the same small calculations as before, that my reduced rank matrix is just this m times m matrix times my original matrix. So that's one way to view how I get from my original matrix to my matrix with a smaller rank. I just multiply it from a left by a big matrix. And this is the proof. You can look at it yourself. It's not important for the sheet, but it's a nice, interesting linear algebra proof. And what does it mean? And I wanted to show you that. What does it mean to multiply a document? So that's now, here we have a 4 times 4 matrix. And that's the last thing I will show today. This is here I write it as a column vector, as a and here I've already written words along the matrix because there's a very interesting intuition here. What happens if I have a document vector in the original space, I multiply it by the 4 times 4 matrix, and I get another vector in the original space, which would be a vector of my reduced rank matrix. And let's just look at this entry here, maybe. This entry here. I mean, what happens is when I multiply this matrix, and it's a particular matrix now, which has almost the identity matrix, and it has a 1 here and a 1 here. And if I do this multiplication, what happens is that this 0 gets replaced by a 1. And why does that happen? It happens, if you think about it, it's, so if I just, let me 2, 3, 4. So this is just name the dimensions here, and this is you will see a second why I'm drawing that in. How do I get that entry? This is the second entry, and I get it by computing the dot product of this with this, right? This is just how I get the, sorry, that was not nice. This is how I get the second entry. It's by computing this times this, and the second entry, this is 1 times 1 plus 1 times 0 plus 0 times 1 plus 0 times 0. So the only thing of value here that gives something non-zero is really this 1 here, right? It's this 1 times this 1. 1 times 1 gives this 1, and the rest is just a multiply. There's a 0 either here or either there. So just by the way, the matrix multiplication works. And this is it's actually easy to see, but it's interesting that this is the intuition, the effect of this one is, what's the effect? The effect is, if there is internet in this document, add web to the result document. That's what it says. If there is internet in this one, add web to the output document. That's exactly the effect, right? If there is internet, if there is internet, yeah, it's always good if there is internet in DI, add web to the result vector DI prime. That's just by the way it works. That's the effect of this matrix, which means you can interpret these matrix look at the off-diagonal matrix which are large, and they will kind of identify synonymy information about. So what this method here figured out, if this would have been the result, is that web and internet are kind of mean the same thing. And you can just compute the matrix, interpret the values like this. So this was an exercise sheet we had in the past. You just compute it. You could actually just do it for fun and look at the pairs where you have large values here, and you will find that there are words which mean the same thing, which is like magic, right? You just computed something, and then you get word similarity without any understanding what the words mean, right? It's just, the thing just gets the matrix. Yes, and that's the last thing. Mm-hmm. Mm-hmm.
Non-zero, because if you do it like we did it before, then you have something like you have that it's maybe old time.
Oh, absolutely. This, I think what you're saying is that computing this is terrible.
And not only computing it, also storing.
Yeah. This is very expensive to compute. Very expensive to compute and store. Yeah, and this is again great to understand it. You would never do this. You would not actually compute this thing and then do this, multiply this here, and actually do it. But it's a great way to understand the method, because what I was saying here in this last part, variant 1, which is just replace the original matrix by the rank 2 approximation, terrible, because all the non-zero entries go away. This variant, terrible, because this is huge, you can't store it, you can't compute it. The second one is actually practical, but they all do the same thing, which means this is a great way to understand, another way of understanding what the method does. What the method does, implicitly, whether you do it that way explicitly or not, it's kind of finding synonymy information between words and adding that to the documents, which is exactly what we wanted in the beginning, right? We said, look, these two words are the same. If there's a 1 here, add a 1 there. And it's really doing that. And you can show it by just looking at the linear algebra a little bit closer that it's doing that. But you wouldn't compute it that way. But if you just take variant 2, it does the same thing, but just, yeah. I mean, that's the method you would actually use. You would just take the representation in the lower dimensional space, which is dense, but if you have a small k, not bad, and then do all the computation there. Which is something, and this is much more than just this LSI and information retrieval. This is a very general idea which you find in all of deep learning also, right? You have a lot of data and you reduce it to some lower dimensional space, get rid of all the noise, and then now you have the information, like the core information, in a very compact form. So that's what's behind this. And that's So I've already shown you what the exercise is. I think it's a super nice exercise. It's a calculation exercise, so no. There are a lot of small things which you can prove if you want to, but the exercise really just calculation. But you have to understand what you're doing. Yes, please.
In practice, what are possible values of k? So if I put a large database, do I still use a k of 2, or do I say I need 5 dimensions?
Yeah, very important question. You also have that in all kinds of learning methods. It's a so-called hyperparameter, which is super important, right? For what do I take, 50, 100, and there all the black magic sets in. And somebody will tell you should take 47. It always gives the best result. So there's no simple answer for that. It's a hyperparameter of the method, which has a big, and there are lots of papers about this, you should choose this or that, but in reality it's very hard to say.
But just to get a feel for the magnitude, so is it like 10 or is it like 1,000? Or it doesn't really totally...
I think in practice, if you really use this method, you would pick it rather small because everything is linear in this. If you take 100, everything takes 100 times. If you take a 10, so you would take a relatively small one. If you think about, I don't know if you know a little bit about deep learning, you have the same word vectors or something. You reduce every word to a vector in dimension k, and the question is which dimension do you take? There you take 300, for example. It's a typical dimension. But it's a value which comes out of nothing. Somebody else might say 100 is also good. But so low hundreds are typical values, but there's no mathematical reason for that. It's just you need a certain dimension to distinguish things. Yeah. But it's a very deep and question and hard to answer. And there's no mathematical reason to prefer one over the other. Maybe there's another question. One thing that's written here, really important. As usual in mathematics, for the simplest thing, you can write 3 pages, then you're doing something wrong, or you can do it in 1 line. So if you end up doing very long calculations with square root of 5 plus pi over e, imaginary numbers cropping up, you're probably doing something wrong. There's a reason for this matrix. It's very well behaved and gives rise to nice calculations if you do it correct. So if it gets very long, very complicated, think, check again, or ask in the forum. You probably did something wrong. Any other question for now? Okay, so have fun with the sheet and see you next week. Bye.